The Lunar Reconnaissance Orbiter was launched 10 years ago on June 18th, and it's still orbiting the moon making fantastic observations. These observations will also help NASA get ready to send astronauts there by 2024. What have we learned from this amazing satellite? Hi, I'm Jim Green, Chief Scientist at NASA, and this is Gravity Assist. This season is all about the moon. I'm here with Noah Petro, and he's the project scientist on a fantastic mission called the Lunar Reconnaissance Orbiter, or LRO for short. And today we're going to talk about our changing moon. Welcome, Noah.
Well, thank you, Jim. It's so great to be here with you today. Well, it's hard to believe that LRO launched almost 10 years ago now, June 18th, 2009. It launched from the Cape down in Florida, and its initial purpose was to chart the moon in 3 dimensions, create a 3D atlas of the moon, identifying safe, scientifically interesting places for future human and robotic exploration. And so its very simple goal, if it's simple at all, was map the moon, find where there might be resources for us to use to sustain lunar presence, exploration, but also to understand what's there at the moon. Let's get the map of the moon that we use to chart our path back to the lunar surface. And so it started with that maybe lofty goal. Now 10 years later, here we are still at the moon. We've revolutionized lunar science thanks to LRO and its suite of 7 instruments.
Right, yeah, it's really been doing fantastic, very healthy, and making some fabulous measurements. I actually believe it's our most capable modern lunar mission ever. What kind of instruments does it have?
Well, you know, the instrument suite, 7 instruments that basically allow us to look at the moon through different lenses. We have, perhaps most famously, our high-resolution camera, the Lunar Reconnaissance Orbiter camera, or LROC. It has a camera on it that can take beautiful images of the lunar surface at a resolution that's completely unprecedented for the entire lunar surface.
Yeah, almost like the size of your coffee table is 1 pixel.
Absolutely, you could see things at the human scale.
Yeah.
But we also are mapping the topography of the moon. We have the best topographic map of any planet in the solar system for the moon.
Topography is the highs and lows, the heights.
The shape of the moon, the measure of the lunar surface, its roughness, the temperature of the surface of the moon. You know, the lunar surface is bathed in sunlight, so it bakes in direct sunlight, it freezes in lunar night, and we can measure the wild temperature swings across the lunar day. We're measuring the radiation environment at and around the moon, as well as measuring water and its various abundances and presence across the lunar surface using multiple instruments. And so we have the 7 instruments that we're using to map the moon and tell us really about the physical properties of the lunar surface and its environment. Now, something that we hadn't planned on was being there for 10 years, and so we're asking new science questions every year. How is the moon changing? How old are surfaces? And so we use those data to really understand what's happened at the moon, not just today, but 4.5 billion years ago as well.
Yeah, so why is the moon important for us here on Earth? Does it have a connection that helps support life?
Well, so that's a really interesting question, and I mean, it goes back to the earliest history of the Earth and the moon system. Earlier on, 4.5 billion years ago, just after the moon formed, it would have been much closer to the Earth and has receded, moved away from the Earth over its 4.5 billion years. We're aware of the tides that the moon exerts on the Earth when you go to the beach and the tide comes in and comes out. Well, 4.5 billion years ago, that swing in tides would have been much greater. The moon is bathing areas along the coastline of the continents, the nascent continents at the time, in water. Water's coming in and out and creating these tidal marshes that would have the ingredients for life. Water,
hundreds of feet high.
Absolutely. You go to the Bay of Fundy, that's what was going on everywhere else on the Earth. And so you have these environments that are being created because of the proximity of the moon to the Earth. And so, I think we can attribute in some small way the flourishing of life in these wet environments because we have this wonderful moon. It's what makes the Earth so unique in the solar system. It's having this large moon so close to the Earth, close to our planet.
It provides another major advantage, and that is it allows us to keep our rotational axis fixed. Like a top that spins and it has enough energy to keep its axis straight up. Some of the planets, kind of spiral around that axis. Our moon has enabled us to keep it fixed, and then The climate variations that we get on a yearly basis can be repeatable year after year after year. So it provides enormous stability on our climate.
Yeah, you compare with the Earth to Mars, and Mars has had wild swings in its climate over relatively short geologic periods of time. We don't see that on the Earth, and so we have the consistent environment that allows life to flourish, as opposed to, say, what would have happened on Mars, where these wild temperature swings do not really evoke an environment for life.
Yeah, that moving of the rotational axis is called the obliquity. You know, what are planetary scientists learning from the moon from LRO?
So one of the basic fundamental insights that we're getting about planetary science, not just lunar science, is how a surface of a planet responds to being impacted, bombarded. Over its entire life, the moon is being impacted by comets, meteors, and so we see this record preserved on the moon. And when we look at other planets in the solar system, even Pluto or Mercury, you see the traces of impacts, or in the case of the smooth areas on any planet, on the few impacts that have happened there. And so we can tie the number of craters on a planetary surface, on any surface, to the age of that surface. And one of the things that geologists love to do is assign ages to things. What happened first, second, third. And all of that understanding of the sequence of events ties back to understanding of what's happened on the moon. And so we're using the data from LRO to refine that understanding, better interpret the geology on any other object in the solar system.
Does that mean the moon is still being impacted?
To this day, every day, there are micrometeorites impacting the lunar surface. We see, in fact, there was an observation of a flash on the moon during the eclipse on January 21st, and that was an incredible event because multiple people saw it. And so we know that these impacts are occurring. The camera, the high-resolution camera in LRO, actually is able to see, by comparing images taken 3 years ago to images taken yesterday, detect those changes, new impacts. And that's an incredible opportunity to understand what a crater does to a planetary surface. The moon, with the absence of an atmosphere, the absence of wind, means that we see these impacts in essentially a pristine state, and we see exactly what happens, and we can calculate the size, the velocity of the object that struck the surface, and through that, gain an understanding of what happens when a planetary object is struck by a meteorite. We haven't seen the large crater yet. We're all eager to find the kilometer-sized crater. Boy,
in our modern life.
Yeah, and the longer we're at the moon, the chance of seeing it is increasing.
A big impact.
I would love to see that. No, don't want to be anywhere near it. That would be a bad day, but I'd love to see it from orbit.
Well, the moon is running block for us.
That's right. Yeah. That's right, and it's a good blocker.
Yeah, it is. So what you're telling me is the history of the solar system through this impacts is really laying on the surface of the moon.
Yeah, it's there for us to read. We've called the moon the Rosetta Stone, the cornerstone of understanding the history of the solar system. And because we have samples from the moon that we can tie to specific features, specific what we call geologic units, areas, we can apply what we understand about that one area to the rest of the moon. And so we have this record of the solar system, this incredible book preserved on the moon, and LRO is helping us read that book.
So is the moon still volcanically active?
That's a great question. And before LRO, if you asked a planetary scientist, when did the moon cease to have volcanism, they would have said about 1 billion years ago. We see evidence now that there may have been volcanism on the moon as recently as 30 million years ago, which is geologically yesterday.
Right around the corner.
Part of the surprise of this is finding these small features that appear to be geologically young, volcanically recent. Well, how do we have a small object that would have cooled relatively quickly have volcanism, sustained volcanism that long? And so we have to revise our models or better understand what our models are telling us about volcanism on the moon. And then, again, applying that understanding across the solar system. Well, if we can have volcanism continue on the moon 30 million years ago, what does it mean for the volcanic history of Mars or Mercury or even Venus? And it's that kind of application of understanding what we're observing on the moon across the solar system that makes the moon so compelling.
Well, the volcanic past of the moon is largely seen on the near side. The large mare, the areas that have huge impacts, that's actually a magma flow that's flown in.
Yes.
What's the backside, the far side of the moon look like?
That's one of the biggest surprises. When we see the far side of the moon, we see almost in a complete absence, apart from very few areas, of a volcanic history. The moon has these two faces, and I wonder if we had been in a situation where the far side of the moon was facing the Earth, that surprising discovery of widespread volcanism on the moon would really have shocked people, in the same way that seeing the absence of widespread volcanism on the far side is a shock. So there's something going on there where we have the two hemispheres of the moon, and they're telling us two completely different stories about what's happened in lunar history.
The evolution of the moon we have to tease out. We have to figure. Some think that the crust on the far side of the moon, which is thicker, hasn't allowed the magma to boil out and go through. But then I think, if you look at the South Pole Aitken Basin, this huge impact region with no magma in it, no volcanic material, maybe it's the fact that the gravitational pull by the Earth is moving the magma more towards the,
just a little
the near side. Yeah, something's going on there we have to tease out. Well, you know, LROC makes some really fantastic high-resolution images of the moon, and it's been seeing all kinds of things, but it's even observed some of the Apollo landing sites.
This is one of the most exciting early discoveries, if you will, from LROC, was imaging the landing sites and seeing these historic locations on the lunar surface. Being able to see the hardware that was left on the moon, the descent stage of the lunar module. You can see the legs, you can see the shadow of the flags at almost all of the Apollo landing sites still there. The rover for the last 3 Apollo missions still parked on the surface, as it was almost 50 years ago. And so we see these traces of our very recent exploration of the moon preserved there. It's quite remarkable, and it's a wonderful connection to the recent history of lunar exploration preserved there on the moon.
Yeah, what I liked is a couple of these of where you even see the backpacks as the astronauts go into the limb before they leave, with the landing legs still there as the rockets are fired off. They throw their backpacks off.
Right, and for me, seeing those backpacks is a remarkable thing. My father built parts for those backpacks.
Wow.
And
so there's a personal connection.
There's an incredible personal connection. He told me a story that when they were finished building, putting all the pieces together, building the backpack, that there's a piece of structural metal in the backpack, and all of the engineers would etch their name into this metal. And so if someday someone goes to one of the Apollo landing sites, returns the portable life support system, the backpack, for display in a museum, and they uncover it, on there will be my father's totally recognizable signature, Dennis Petro, recorded on the lunar surface.
Oh, that's wonderful. Well, what's fascinating also about that is they got rid of the backpacks because they wanted to make room for the rocks, the lunar material. So if you're going to take weight up, you want to get rid of some weight, and that was an easy thing to do.
Absolutely. You never need to use it again. You leave all that on the lunar surface, and you bring back the real treasure of the moon, which is the Apollo samples.
What are some of the other things about the moon that really excites you that LRO is uncovering?
Well, you know, there's so many things about the moon that, even though it's essentially in our backyard, that we are just discovering for the first time now, thanks to LRO. And I think one of the things that's most compelling about the moon is the unique environment that we see at the lunar poles.
Wow.
You know, these very, very cold areas at the poles, some of which are the coldest measured temperatures in the entire solar system.
And that's because you can measure temperature.
That's right, we can measure
from LRO.
That's right, the Diviner instrument on LRO can measure the surface temperature, and we see these very, very cold environments that have potentially water ice in them, certainly have water that we've measured. It's a different environment, and I don't know that we really comprehended how unique that environment is in our entire solar system. We have this deep freezer 3 days away at the poles of the moon, and who knows what's recorded in there. Billions of years of activity in the solar system, of lunar activities recorded and archived there at the lunar poles.
So in other words, if you had an ice cube and it sat on the moon and the sunlight was beating down on it, it would easily disassociate itself, turn into vapor, and dissipate away. But in an area like a crater that is hidden from the sunlight, this is that concept of permanently shadowed. How do you guys figure out it's permanently shadowed?
So the really great thing is, by having been at the moon now for so long, we can image the moon repeatedly. And we can make these high-resolution maps of the shape of the moon. And so we can either image places that are sunlight, not sunlight, dark, not dark. But we can also map the moon and get an understanding of the shape of the moon and propagate. We can plan, say, well, what's that going to look like in a day, 2 days, 3 years, 30 years? And so we can basically predict areas on the moon that will never receive direct sunlight, maybe receive direct sunlight for a few days as the moon slowly wobbles around the Earth and around the sun. But we can and essentially use our knowledge of the shape of the moon to understand what will be in darkness in the future, but also how that darkness may have been a billion years ago, how it propagates throughout geologic time. And so we develop this understanding of the sort of how the environment at the poles has evolved over the entire lunar history and how it will evolve. It's especially important for future exploration. If you want to go to the poles, you need sunlight to power your batteries, to power your rover, what have you. You want to be in sunlight, but maybe you want to go into an area that's been in permanent shadow for a billion years. We can tell you where to go.
And it has a resource. It's got water, and water, H2O, can be used for a variety of things. You can drink it, you can breathe it, disassociate it, but you can also use it for rocket fuel. Yeah. So it's like a fuel depot.
Absolutely, and it's sitting there on the surface waiting for us to tap it, to understand it.
Yeah. Now, when you talk about the shape of the moon, it's spherical, but in actuality, gravitationally, it's not spherical in the sense that it's uniform everywhere. What's that all about?
So, the phrase that we like to use is lumpy. It's not a very technical term, but the moon's gravitational field is irregular. We know that there are areas, particularly under those volcanic lava flows on the near side, underneath these large impact craters that are they're called mass concentrations, mass cons. And so the gravitational pull under those areas, because it has so much more mass, is a little bit greater. And so for an orbital spacecraft, they're constantly getting pulled by these concentrations of mass. And so uneven gravitational field can make it very difficult to stay in lunar orbit for long periods of time. Now, LRO's been able to do it because we've found ourselves in a really elegant orbit that goes low over the South Pole, high over the North Pole, where the constant tugging of the gravity of the moon is a little bit subdued.
Or averages out in some way, so that you can find a stable orbit.
And allows us to be there for so long. But, past missions that stayed in a lower circular orbit that passes, 50 kilometers over the whole surface of the moon, they could only stay there for a few months if they didn't do constant maneuvers. And so, we stayed in this low orbit for a period of time early in our history, and then went into this more stable orbit so that we could have this wonderfully extended mission.
Well, it's still there and it's still working great. And there's a variety of new space agencies coming along that want to go to the moon. They want to land on the moon. Where do we fit in? Are we helping them?
Absolutely. So the wonderful thing about our data is, first of all, it's made available to the world, not just to scientists, not just to American scientists, but around the world on a relatively short time scale. And we're excited for the opportunity to work with partners to get to support their identification of safe landing sites. And so our data is made publicly available. We've worked with international agencies through agreements through NASA headquarters to say, well, okay, you want to go to the surface, you want to go to this particular location, we'll provide the data to you and everyone else so that you can plan the best possible mission to the lunar surface. And we're really starting to see that come to fruition, and hopefully in the very near future, we'll start to see some of these partners get to the lunar surface.
Yeah, so we're partnering with a variety of commercial entities that want to land on the moon, and we want instruments on those spacecraft and landers and even rovers. They're going to be needing LRO data, so keep it healthy, Noah.
Absolutely. Well, every day
I'm thinking
how can we keep this mission going? Because I cannot wait for the chance to get one of these landers, get a rover on, that we have an instrument on, and make coincident observations. Is a great opportunity for joint science between LRO, the Artemis mission, and once we get to that point, that will be a really exciting new era for lunar exploration.
Well, your own personal research uses multiple data sets. How does that help our understanding of the moon, and what are you doing in this area?
Well, what excites me the most, particularly about the moon, is that we have samples. We've got chunks of rock from various locations on the moon. And what I really enjoy doing is looking at these Apollo landing sites and saying, well, let's take all that we know about this one area from orbit. So we take the high resolution images and we take the data that we get from other instruments, and let's put those samples that we got into a context of the remote data sets.
You know where they came from.
We know exactly where they came from. We say, well, this rock came from this point, and how can we use that information to better understand what happened on the other side of the moon? So we look at the Apollo 17 landing site and the boulders that were sampled there. Where do those boulders come from? And we can trace, thanks to those high resolution images, how those boulders roll down the hill.
Okay.
Where did that hill come from? Where is it ejected from a basin 1,000 kilometers away? Okay, well, where did that come from? And so we start unraveling the history of the moon using the remote data and the samples together. And that really helps tell us this comprehensive story of quite simply the last 4.5 billion years of lunar evolution.
Well, what was your biggest surprise from the Lunar Reconnaissance Orbiter?
Well, so far, and there have been a number, and every day I feel like I'm being surprised by the latest discovery, but honestly, for me, it was the identification of these LRO-era craters, seeing changes on the lunar surface. And, for my entire career, we're trained with this thought that the moon is this static object in the sky, but now we can actually quantify changes on the lunar surface. Every instrument on LRO has detected changes in some way, whether it's a new crater or it's the change in abundance of water on the surface. We are able to see the moon changing gradually beneath our philosophical feet on the spacecraft. And so the moon is still largely unchanging, certainly nowhere as dynamic as the Earth or even Mars or Venus, but we are able to quantify how it's changing. And that's important because, well, it tells us how the planet is working, how the moon is working. And again, by extending that understanding to other objects in the solar system, we know that other things are changing as well. And by understanding the changes that are occurring on the moon, we can better understand the dynamics on any other object in the solar system.
For me, what was really exciting about the LRO observations as we study the surface of the moon in great detail from orbit, we're finding new features, things that we call like skylights.
Yes.
Things that we call like swirls. What are those?
So yeah, the skylights and the swirls are this great group of surprises on the moon. The skylights are these collapsed lava tubes where we get a glimpse into what may be a very extensive lava flow that once went underground and is now a tube. And so we see into these areas, these voids that may be, kilometers wide, hundreds of meters deep. And these are micro environments. We talked about the environment of the poles of the moon. Well, these skylights, these lava tubes, are going to be their own unique environment. They're getting heat that's coming from the deep interior of the moon, percolating up through the crust. They're going to have a reservoir of the gases that have been floating around the moon, but also a lunar surface that's not been exposed to solar wind, what it's going to look like. Then you talk about the swirls. Swirls are these amazing expressions of magnetic fields on the lunar surface that have kind of protected the moon from getting a sunburn, if you want to think of it that way. And there are these wonderful, wispy features that have been, sort of anomalous for the better part of 50 years since we've really been able to image them at high resolution back in the 60s, to now these really interesting dynamic environments that, boy, are just begging to be explored.
Are there any misconceptions about the moon that you're particularly interested in correcting?
Absolutely. I love talking to the public about the moon, and there's a misconception that, well, we've been to the moon, so we know everything. And I think as we've talked about now, there are so many wonderful mysteries that are important for understanding not just the moon, but the entire solar system recorded on the lunar surface. So I think the most important misconception is that we know the moon. Well, we know a little bit about the moon, just enough to be dangerous, and just enough to tell us that there's a lot of really interesting and compelling places to go.
What's next for you with respect to lunar exploration?
Well, as you said before, what's next is keeping LRO alive. We're in the process of proposing for more operational time at the moon, but we would love to see some missions come join us. And so we're supporting these commercial landers. We want to see them get to the surface successfully and conduct good science. And we'd love to see other NASA-led missions get to the moon as well. And so we're trying to put together a case for what we can do, not just on the lunar surface, but from lunar orbit. As well as I'm really excited to see what happens with continued study of lunar samples. And so personally, I'm trying to combine all of these interests of mine, the understanding of what happens and what we can tell about the moon from orbit, but also what we can learn from the samples. And so tying all those things together is what keeps me busy, but also engaged and excited about what's to come with lunar science.
Well, I always ask my guests, what happened in their career? What happened when they were young that got them excited about being a planetary scientist, that really accelerated them forward to become the scientists they are today? So Noah, what is your gravity assist?
I had multiple gravity assists, like many successful missions in the NASA portfolio. And I talked about my father's involvement with Apollo. And that was this moment that sort of, there's a human face to exploration. That's really interesting, and that got me interested in NASA. In high school, I had some of the best science teachers you could ever ask for. In particular, earth science teachers, geology teachers, who got me passionate about understanding the Earth and what rocks can tell us about the history of the Earth and what our understanding of the Earth means for our knowledge of how the solar system works. So I went off to college thinking I'd become a high school science teacher. And early in
Really?
my first, because I saw those teachers having so much fun, I said I wanted to do that. I had a professor who stepped in to teach my intro geology course for a week my freshman year, and he said, we're going to talk about the moon for this week. And I thought, wait a minute, you can do geology on the moon? And that was Professor Gene Clough. And he says now that, the first day that I had that class, I went up and talked to Noah, and we haven't stopped talking since. And that opened my eyes to the idea that you can do geology on other planets, particularly the moon, which I was really interested in.
And learn a lot.
And that put me on that path, and Gene encouraged me to apply for summer internships, which I would not have done otherwise. And so I really took his mentorship to heart. And one of those summer internships, I ended up working at the USGS in Flagstaff with Lisa Gaddis. And she said, well, no, if you like this planetary science thing, why don't you think about going to work with Carly Peters at Brown? I said, okay, Lisa, I'll do that. Sure, I always do what I'm told.
Yeah, right.
And then I went off to work with Carly. And of course, at that time, this is 2001, lunar science was, one of many fields,
Sure.
but Mars was a really hot object
Mars
at the
was
time.
hot, yeah.
And so I was this outlier. I've always been an outlier, but I was really an outlier then. Oh, you're interested in the moon. And so I've had these people who just nudge me in the right direction, give me the advice that I needed to hear, and I've taken it. And that's what's got me to this day. And it's not one thing in particular, but all of these little moments in life have just pushed me in the right direction.
Well, Noah, I really want to thank you for spending time with me today to talk about the moon, because this is the year of the moon.
2019.
Yeah, and you and LRO play a major role in it. Thank you very much.
Thank you, Jim.
Hey, Gravity Assist listeners. This is producer Liz Landau. Our friends over at NASA Goddard Space Flight Center are working on a new podcast called NASA Explorers Apollo, a series about the people behind past, present, and future lunar science. They've also been collecting stories from people like you, reflecting on the 50th anniversary of the Apollo 11 moon landing. If you'd like to share your story, record an audio clip and send it to apollostories@mail.nasa.gov. We'll end today's Gravity Assist podcast with a memory from a listener named Ginny O'Donnell in Danville, Kentucky, who tells us about her homemade moon-made lemonade and Kool-Aid.
Hi, NASA. It's me, Ginny. 50 years later, I got in such trouble after the moon landing. So here's what happened. The morning after, my brothers, Bucky and Monty, and my next door neighbor, Melissa, and our friend Reedy and I decided to celebrate with a lemonade stand. And we used up all of my grandmother's aluminum foil to make space helmets and Moon Maiden antenna. Remember the Moon Maiden from Dick Tracy? So she was really beautiful and we loved her. And then we made lemonade and Kool-Aid using all of my grandmother's sugar. And we set up our stand on the side of the road, and we called it Homemade Moon-Made Lemonade and Kool-Aid. And we thought we were just the best and the smartest kids on the whole planet Earth, until my grandmother got home, and my goodness, she was not happy. We had used all of her precious aluminum and all of her precious sugar, and goodness knows how many lemons, and those little packets of Kool-Aid that were just stashed for special occasions. I don't reckon I sat down for a week. But anyway, I love this memory of the moon landing so much, and every year when this comes up, I think of it as the homemade moon-made lemonade and Kool-Aid, and I cheers all of my little friends who helped me make it happen. So happy 50th, NASA. Love you, Jenny.